My name is Jinuk Lee, and today I will be presenting my work titled Evolving Pareto-Optimal Reasoning Paths in LLMs. The core question we ask is, when an LLM solves a math problem, what does it mean for a reasoning path to be good? What is the good reasoning path? So we argue the answer is inherently multidimensional, and we build a framework around that insight. Let me start with the problem. Like, LLMs are increasingly powerful at mathematical reasoning, like chain of thought prompting, reinforcement learning with verifiable reward, and like the result of Python code execution, and test time scaling with verifier, which is trained by processor outcome signal. But these methods mainly focus on single scalar reward. Typically, that scalar is answer accuracy. But think about something like a model can reach the correct answer through a logically brittle path, like one that relies on spurious correlations, skips unjustified steps, or is simply verbose and redundant. It only asks, is the final answer right? So we argue this is the wrong question. An ideal mathematical agent should balance multidimensional things simultaneously, like accuracy, is it correct or not, and logical coherence, does each step follow from the last, and efficiency, is the proof concise and non-redundant. Yeah, like these objectives are often in tension. A maximally accurate path may be verbose, a maximally efficient path may skip intermediate steps. Like, no scalar can capture this trade-off properly. So what we need is a framework that navigates these competing objectives, like goals. So instead of asking like find the best reasoning path to solve this problem, we ask find the Pareto optimal front of reasoning paths. We treat each reasoning path as an individual in a population, evaluated on 3 objectives simultaneously, and use an evolutionary algorithm, in this situation specifically NSJ2, to iteratively evolve the population toward the Pareto front. No single path wins. Instead, we get a diverse set of paths representing different trade-off profiles, like accurate but verbose, efficient but less certain, and everything in between. So here's our full architecture. Yeah, the system learns this system learns in a generational evolutionary loop with 3 phases. Phase 1 is multi-objective optimization. Each reasoning path P is a sequence of logical steps, like consists of S0, S1, S2, ... Sn. We evaluated it on the objective vector, like accuracy, coherence, efficiency. Like accuracy is verified by symbolic solvers or format tools, and coherence is assessed by LLM itself, and efficiency is measured by like counting redundant or non-contributing steps. So our NSGA2 algorithm ranks these paths into Pareto fronts based on dominance. Like path P1 dominates P2 if it's better in at least one objective and no worse in all others. And yeah, dominance, measuring dominance. And then we also compute crowding distance to maintain diversity. Yeah, our formula is in our paper, so yeah. This anyway, these rewards paths that occupy unique regions of the objective space, ensuring the framework explores geometric and hybrid proof strategies simultaneously. And next page 2 is LLM guided variation. Here's what makes our approach different from standard evolutionary algorithms. We don't use random mutation. Instead, the LLM itself is the genetic operator. Like in case of crossover, the LLM is prompted with two parent passes and asked to identify successful sub-proofs from each, then integrate them into a stronger offspring. Yeah, stronger offspring finally left. And mutation, like in case of mutation, the LLM is shown a single pass and asked to identify its weakest step, then regenerate it with higher precision, guided by textual feedback. And yes, the key point is LLM itself. And page 3 is parallel verification. Each candidate is one of the test time scaling techniques. Like each candidate is evaluated concurrently by 3 modules, like verifier, critics, analyzer. The penalization is the key point. The penalization is what makes the evolutionary loop tractable at scale, like step 1, page 1 and page 2. So for evaluation, we used Gemini 3.1 Pro as the LLM backbone, basically. So, and selected 3 classic geometry optimization problems. These were chosen because they sit at the intersection of continuous optimization and discrete logical constraints, like a setting where standard gradient decoding reliably struggles to solve this problem. The 3 problems are: first one is the moving sofa problem. What is the maximum area shape that can navigate an L-shaped corridor? Second one is the Erdős accuracy's happy ending problem. How many points in general position guarantee a complex K-gon? Third one is packing in a dilate. What is the minimum scale factor to pack n copies of shape inside a scaled copy of itself? For each, our framework was initialized with a diverse LLM generic population and learned for multiple generations to observe convergence toward the Pareto-front path. Yeah, Pareto-front path optimal. And okay, starting with the moving sofa problem. Actually, in 1992, Garber constructed an optimal sofa with area C approximately 2.2195, which has since been proven to be the true maximum. Our framework, running its evolutionary search, so successfully converged to this known optimal value C, 2.2195. And additionally, we also solved the dexterous sofa problem, which is extended version of this moving sofa problem. The key observation here is that the Pareto-front selection consistently surfaced solutions that were both accurate and concise. Yeah, not just solutions that maximize accuracy alone. For the happy ending problem, we ran the framework with convex k-gon count as the objective to minimize for values of k up to 8. The framework reliably produced 2 to the k minus 2 point configurations containing no convex k-gon, which is exactly matching the non-external constructions. Degenerate configuration were correctly penalized to enforce general position, pushing to 2k minus 2 and plus 1 points was unsuccessful, consistent with the theoretical lower bound being typed. For packing a dilate problem, our framework generated geometrically diverse configurations whose scale factors closely approach the theoretical lower bounds given by packing density arguments. It is kinda great result. This demonstrates our framework's flexibility across different geometric problem types. To summarize, we introduced a self-evolving reasoning framework that treats LLM reasoning path generation as a multi-objective optimization problem. By integrating NSG2, we navigate trade-off between accuracy, logical coherence, and efficiency. Also, the LLM acts as an intelligent genetic operator, like conducting crossover mutation. And not just a generator, but like recombinator and refiner. Results on 3 geometric optimization problems demonstrate convergence to non-optima and reproduction of extremal constructions using Gemini 3.1 Pro as the backbone. But however, I'm gonna be direct about the current limitation. I want to be direct at limitation. First one is like scope of experiments. Like tree problem is a narrow evaluation. We do not have results on standard benchmarks like MES or GSMA AK or Olympiad or AIME. More extensive benchmarking is and like more open-ended problem is required to establish statistical robustness. Second, our results they don't establish new ones. Like the contribution at this stage is the framework itself and is the ability to converge on known stuffs, known results, not novel mathematical discovery. But we view this as validation. We view this as the validation, not the ceiling. Third one is the coherence of objective relies on LLM-based evaluation, like which might introduce imprecision. Tighter integration with formal proof assistance like lean or COQ can be better next step. These three are honest limitations, and they point directly to the future work, and I'm gonna improve my work. Thank you for listening, and